The topic for today's presentation is Introduction to Quantum Computing Gates, State Vectors and Block Sphere. Uh, this first slide, I intend to give a background where quantum mechanics is taught to most students of our engineering students for decades. But the foray into quantum computing only began around 3 decades ago. The one feature that distinguishes the quantum computing is how we look at a bit. The classical computer bit, which exists in the form of a 0 or a 1, so inconsequentially in our classical computer, it is represented as a complex number called the qubit or the quantum bit in the quantum computer. That is, a 0 is represented as a plus ib, where I is equal to square root of -1, and a and b are real numbers. Now, this method of representing 0 and 1 was discovered almost 1 century back. And as infants, we always learn that a small object, right from our childhood, object exists in a unique place and in a unique, well-defined state. But quantum science proves that this is false for very small objects. A microscopic object can hazily be more than one place at one time, and it simultaneously can be in one location at the same time. This is a phenomenon called superposition, and quantum uses superposition in a very fundamental way, where rather than having one computer in one state at one particular time, a quantum computer can exist in many states simultaneously, reflecting parallelism. So that means we have to write programs and algorithms for parallel machines. And quantum computing assumes enormous significance because the government of India launched the National Quantum Mission in 2023 with a 6,000 crore rupees of corpus. Now, I am not here to talk about quantum and its background. Rather, I will delve into a more fundamental way how a qubit is represented in the form of gates. Contrary to what popular science implies, there is nothing random or unpredictable about this process. Mathematically, a qubit is a matrix. That is, as I already said, a qubit exists in the form of a complex number, a plus ib. And so far, I have been listening to the talks since the morning. And one way or the other, we are all dealing with classical machines, classical computing, bits and zeros. But quantum is in a completely different level altogether. For example, 0 is represented as a 2 by 1 matrix with a 1 and a 0. Whereas 1, the bit 1 is represented as a vertical qubit, 0 and 1. You see the difference? And this happens in a 1 qubit computer. And if you have to flip the bit from 0 to 1, we have to go through a complex process called applying the Pauli's X gate or the NOT gate, where you multiply the Pauli X gate with 1 to make it a 0. And as I said, 0 for a 1 qubit computer is a 2 by 1 matrix, whereas representing 0 for a 2 qubit computer, it is becoming more complex. It becomes a 4 by 1 matrix. On the right hand side, you can see how I have represented 0, 0, 0, that is 0, 0, 1, 1, 0, which is 2, and 1, 1, which is 3. So each of them is a complex number with the imaginary parts as 0. The geometric representation of a single qubit I have depicted in this diagram, where you have the qubit 0 representing it in the North Pole and the qubit 1 being represented in the South Pole. And you have two angles, theta and var phi, as we have shown here, which describes one qubit in three-dimensional space where the radius is 1 centimeter for this sphere. Now, I have spoken to you about how gates are represented in quantum computers. For running any quantum algorithm, we require the Python programming language. And I have, though time would, if time permits, I would have done it. But are you able to see my uh, Python screen?
No, we just see the slide, and I think probably we should just stick with the slides given
Okay,
the
sir.
time.
Okay, sir. Yeah. I understand, sir. Understand. So, are we able to see the screen now?
Yes.
Yes.
Yeah. This is in the Python language, and you require lines and lines of code to represent a single qubit. So, and this is the block sphere where I have represented a 1, and here is another block sphere where I have flipped the qubit to 0. Now, this is all I just wanted to convey in this brief talk. The takeaway is a qubit is represented in the form of a complex number in a matrix. And for writing algorithms in quantum, you require the Python language and a Jupyter notebook. That's all from my side. Thank you.